It's the final homework assignment of Honors Physics at PW, homework number 30, elastic collisions. And the key here is that it should be so that in all of these questions that we see in this assignment, that they all imply in one way or another that when the collision takes place, the collision is elastic. That is to say, the energy is conserved. I don't need to concern myself with 1/2 mv squared plus 1/2 mv squared equals 1/2 mv squared plus 1/2 mv squared, because I've already done that in class, and I've discovered that when I apply the law of conservation of momentum and the law of conservation of energy together, that I get an additional equation. And that equation is that VA minus VB, the initial velocity of A minus the initial velocity of B, is equal to VB prime minus VA prime. What I like to do is recognize there that I've sort of swapped the order around. So I'll say it again. VA minus VB equals VB prime minus VA prime. So when I'm confronted by one of these elastic collisions, it's going to require me to write the law of conservation of energy, or pardon me, the law of conservation of momentum, that is, MAVA plus MBVB is equal to MAVA prime plus MBVB prime, but also I'll need to write VA minus VB equals VB prime minus VA prime to solve. So this first problem on the assignment gives me a couple of different looks at elastic collisions. I have two objects, they have equal masses. Now there's a bit of a special thing about objects that have equal masses that collide elastically. When they have equal masses, it turns out, and you can solve this to prove it for yourself, it turns out that they exchange velocities when they have equal masses. Now later on in this particular item 1 on homework 30, they'll change the masses up. But for the moment, they have equal masses and they collide elastically. So let two objects of mass m collide. Object 1 has an initial velocity v, and object 2 is initially stationary. What's going to happen when they collide is object 1 is going to stop, and object 2 is going to continue on with the velocity that object 1 had initially. When the masses are equal in an elastic collision, the two objects simply exchange velocities. Now suppose that the collision is perfectly inelastic. Well, what that means is that they stick together. This is a problem that we've already solved. This is a problem where the energy is not conserved, but they stick together as one object. So that they're talking about object 1 and 2 instead of object A and B. So I'll say that M1 times V is equal to M1 plus M2 times V prime, and I solve. That is, the velocity after collision is equal to M1 divided by M1 plus M2 multiplied by V1. We're still in a case here where the masses are equal, so that works out to be quite simple. In fact, it'll turn out that the velocity after collision is just half. V1 and V2 will have the same velocity because they've stuck together and now move with a mutual velocity together. Now assume that the mass of object 1 is 2m. Well, this is where things start to change a little bit, and I might want to write out some equations in order to solve. The two equations that I'll write for part C are M1 V1 plus M2 V2 is equal to M1 V1 prime plus M2 V2 prime, and V1 minus V2 is equal to V2 prime minus V1 prime. That's as far as I'm going to go with this because I've already given too much away on this problem so far. Part D is the same. I've given different masses, and so it's all going to work out. When you write these equations, since the masses are given as m and 3m and 2m, when you write the equations out, you'll see that the mass will appear in every equation, and you'll simply cancel the masses. Hopefully, we'll move on to something more interesting here. An air track glider undergoes a perfectly inelastic collision with an identical glider that's initially at rest. So the gliders are identical. So this is a condition that I've said that I have two objects of equal mass that are going to collide. They're simply going to exchange velocities. So what fraction of the first glider's initial kinetic energy is transformed into thermal energy in this collision? Well, the collision here that's described is perfectly inelastic, so actually I have to edit my comments here because they're going to stick together, which means I'm simply going to calculate the final velocity as the mass divided by the sum of the masses times the initial velocity. And so do that and calculate the initial kinetic energy and calculate the final kinetic energy and divide the initial kinetic energy by the final kinetic energy, and that's the ratio that they're talking about here in the question. Problem 3, I'm hoping for some elastic collisions. Oh, here we go. Two balls undergo a perfectly elastic head-on collision with one ball initially at rest. If the incoming ball has a speed of 200 meters per second. 200 meters per second. Gosh, that's fast. What is the final speed of the incoming? Pardon me. What is the final speed of the incoming ball if it is much more massive than the stationary ball? Well, I don't really need to write down a lot of equations to work this out. Imagine that I have a ball that is super massive, moving with a large velocity, 200 meters per second, and it collides with a very small ball. Well, its velocity is not going to be changed by much. So I might guess that the velocity v1 is 200 meters per second. What is the final direction of the incoming ball with respect to the initial direction? Well, it's going to be in the same direction because this far less massive ball is not going to be doing anything to stop it. What is the final speed of the stationary ball if the incoming ball is much more massive than the stationary ball? Is that not what they said in the first part? What is the final speed of the incoming ball if it is much more massive than the stationary ball, is what part A says. Now in part C, what is the final speed of the stationary ball if the incoming ball is much more massive than the stationary ball? Okay, so it's the same physical situation. But now I have to consider that the masses are much, much larger. So consider, I don't want to give too much away because it's your responsibility as a student to solve the problem, but consider that the initial velocity of the incoming ball is not going to change much. And then use that in our equation for the elastic collision. That is the equation that says that the velocity of A minus the velocity of B is equal to the velocity of B prime minus the velocity of A prime. You need to write out that equation and consider what happens when the velocity of A does not change. Then you'll be able to work out the final speed of the stationary ball. It turns out that speed should be significantly large. And the same is true for the rest of the parts of this problem. It's all working out according to that conservation of energy equation. What is the final speed of the incoming ball if the stationary ball is much more massive than the incoming ball? Well, the incoming ball then is going to bounce off the stationary ball, and the velocity of the stationary ball is not going to change much at all. What is the final direction of the incoming ball with respect to the initial direction of the stationary ball is much more massive? Well, the incoming ball is going to turn around and go in the opposite direction. See, I can answer these things according to my intuition. What is the part G here? What is the final speed of the stationary ball if it is much more massive? Well, it's going to be very nearly equal to 0. What is the final direction of the stationary ball with respect to the initial direction? Well, the ball was initially stationary and it gets hit from the left. Then its direction must necessarily be to the right. Question number 4 in this assignment, ball 1 with mass of 140 grams, traveling, well, these are my numbers, by the way, your numbers are probably randomized, traveling at 15 meters per second, collides head-on with ball 2, which has a mass of 320 grams initially at rest. What is the final velocity of ball 1 if the collision is perfectly elastic? So what I'm going to do for part A here is I'll write the conservation of momentum, which is m1 v1 is equal to m1 v1 prime plus m2 v2 prime. But also I'm going to write the elastic equation, because I'm told here in part A that the collision is elastic. And I'll write that V1 minus V2 is equal to V2 prime minus V1 prime. And I'll solve those two equations simultaneously. They want me to compare it in part B to a situation where they are perfectly What is the final velocity? Oh no, final velocity of ball 1, final velocity of ball 2 in part B, and in part C, what is the final velocity if it's perfectly inelastic? So when I get to part C, it's going to say, okay, we've solved the elastic version of the problem. What will we get when we solve the perfectly inelastic version of the problem? And that version of the problem is when the two things collide and they stick together, which is a problem that we've already solved. Here, I don't need the elastic equation because the conservation of momentum alone will solve the problem because the two masses stick together and become one. What is the final velocity of ball 2? Well, it's the same. If they're perfectly inelastic, then the final velocities of ball 1 and ball 2 are the same. Last problem of homework in honors physics. Congratulations. A 49-gram marble, be sure to convert to kilograms, as in the previous problem. A 49-gram marble is 0.049 kilograms, moving at 2 meters per second, strikes a 0.03 kilogram marble at rest. Assume that the collision is perfectly elastic and the marbles collide head-on. What is the speed of the first marble immediately after collision? What is the speed of the second marble immediately after collision? Well, once again, I'm going to be using the equation of the conservation of momentum, which is m1v1 is equal to m2v2. M1v1 plus m2v2 is equal to m1v1 prime plus m2v2 prime. But because I'm told explicitly that the collision is elastic, I can also use that v1 minus v2 is equal to v2 prime minus v1 prime, and I'll solve those two equations simultaneously to get my answers to part A and part B. And that's it. That's the end of all of the mastering assignments for honors physics. Sing Hosanna.